laser industry specifically.
It has changed dramatically.
The field of biophotonics was just getting started.
The first instrument that I bought was a microwave spectrum analyzer.
It's time to shed light on our universe. This is All Things Photonics, a podcast about the physical science of light. Join us as we explore the latest in lasers, optics, spectroscopy, and microscopy. Each episode, you'll hear from leading voices from across the photonics landscape. We're brought to you by Photonics Media.
This is Associate Editor Joel Williams. Here are this week's top stories. An infrared transmitting polymer based on common low-cost materials may lead to low-cost night vision lenses that retain focus while imaging at variable distances. The polymer, developed by researchers from the University of Tsukuba, keeps its shape after stretching. Chemists at the University of Groningen have designed a near-infrared light-powered rotary motor, the type that can be used to deliver autonomous motion to a system, or to ensure that a system responds to a prompt on command. The chemists administered near-infrared light to their molecular motor through an antenna. Quantum theorists from Griffith University and Macquarie University, both in Australia, used quantum mechanics to overturn an assertion about laser coherence that has been the common belief for 60 years. The research shows that it is possible to build a quantum-limited laser using superconducting technology, which is currently used in quantum computing. Researchers at ETH Zurich have demonstrated a method for the delivery of multiple laser beams precisely to their intended locations from within the physical architecture of a single chip. The method is stable enough to allow for delicate quantum operations. And finally, researchers at the University of Rochester and the Fresnel Institute in France developed a method for visualizing molecules' position and orientation in 3D, as well as their oscillations. The technique could allow for greater insights into the biological processes involved when a cell and the proteins that regulate its functions react to a COVID-19 virus. Up next, news editor Jake Saltzman speaks with Andreas Tuennermann, head of the Fraunhofer Institute for Applied Optics and Precision Engineering and director of the Institute of Applied Physics at the University of Jena. I'm Joel Williams, and this is All Things Photonics.
Today's episode is sponsored by PI Physik Instrumente. PI manufactures world-class precision motion control, alignment, and automation systems, including air bearings, hexapods, and piezo drives at locations in North America, Europe, and Asia. PI's customers are leaders in high-tech industries and research institutes in fields such as photonics, biotech, life sciences, semiconductors, and aerospace. Visit www.pi-usa.us. And by COMSOL, the leading developer of multiphysics simulation software, which includes tools for building and deploying simulation apps. COMSOL's wave and ray optics capabilities are used for modeling, imaging, and sensing in consumer electronics and biotechnology, information processing and communication systems, and more. See how the COMSOL software fits your optical analysis needs at www.comsol.com.
Our guest today is the head of the Fraunhofer Institute for Applied Optics and Precision Engineering, as well as director of the Institute of Applied Physics at the University of Jena. He's also an SPIE Fellow, recipient of the Berthold Liebinger Innovation Prize from the Berthold Liebinger Foundation, and just this summer has played a pivotal role in the development of Fraunhofer's new quantum application laboratory. Welcome, Dr. Andreas Tuennermann.
Hi, nice to meet you, especially in these interesting times we are facing due to the coronavirus.
No question about that. So I want to get into talking here in the present, but I want to start with a bit of a flashback. It's been about 3 years since Fraunhofer and partners inaugurated Fraunhofer IOF's Fiber Technology Center. Can you tell us a little bit about the ongoing progress, I should say, initiating at the center? And what can we look forward to as we move ahead here into the next decade?
Okay, it's a pleasure. So this Fiber Technology Center has been started in a collaboration with the University in Jena and also the Institute of Photonic Technologies in Jena. We merged our activities in glass chemistry, in process technologies, handling glass, doing, for example, fiber drawing, but also in laser physics. And the result was, in fact, that we are now able to develop and manufacture special fibers in a wide range, starting from hollow core fibers, for example, multi-core fibers, but also special ultra-low loss fibers to be used, for example, for quantum technologies. And I think we brought in specific new ideas to open up new avenues in telecommunication, in biomedical industry, in laser science, but of course also in quantum technology.
And on that note of collaboration, in August of this past year, you were part of a collaborative team that demonstrated the ability to laser cool silica glass, and it was the first time it's been done. Can you tell us about that work with the University of New Mexico, and in broader terms, what that says about laser cooling capabilities?
Yeah, in fact, this is a result of our work here in the Fiber Technology Center, especially in the field of glass chemistry. Starting with a collaboration with the University of New Mexico, we asked ourselves if it would be possible to optically cool fused silica. And to do this, it is very important that you have a low loss material with high quantum efficiencies, for example. And in the discussion with our colleagues in New Mexico, we learned that our glass we are using for the manufacturing of the high power laser fibers should fit to these requirements. And we realized in a close collaboration with our colleagues the first cooling of fused silica solid state material. And I think it was a pioneering experiment where we brought in and merged the different competencies in laser technology, in glass chemistry, but also in optical spectroscopy from our different groups and realized this interesting thing.
You say it's pioneering. Tell us a little bit about the potential of the work and what it tells us about laser cooling capabilities as we move into the next phase of research.
Well, laser cooling is technology which has been developed several decades ago, and it has been used so far for atoms, for ions, and also for molecules, small molecules, in fact. And the work related to the cooling of solid-state materials is quite new. If you cool some solid-state material, of course, you have non-radiative relaxation processes. And these are loss mechanisms which limit the cooling efficiency within such a material compared to a single atom or a single ion. And this is a technology which, from my point of view, will be very important to accelerate future developments in quantum technology.
I want to jump gears a little bit here and ask a manufacturing-themed question, a German manufacturing question. German manufacturing, especially that which involves lasers, is really quite well established and has grown significantly in the last 20 years or so. And paramount to that growth in industry has been the ability of laser education and laser physics to support the technological ingenuity. I'm curious how laser education and laser physics keep up with the rigorous and increasing demands of laser applications in industry.
Oh, that's a good question. So I think we have seen, especially in the past years, new developments in laser processing, for example, driven by the application of ultra-fast lasers in micromachining, and of course also accelerated by new developments in laser physics. For example, we recently realized femtosecond lasers with average powers in the 10 kilowatt regime. There are new applications coming up in industry, especially in the manufacturing industry, based on these advances in laser science. And the question is, of course, how can we bring these fundamental knowledge about lasers, about laser-matter interaction to real-world applications. And education is a very important point, I have to say. There is a commitment from the German laser industry, in fact, to support specific education programs. And at the universities in Karlsruhe, in Erlangen, and in Jena, we have established international photonic master programs and PhD programs, which directly focus on the needs, the requirements of the industry. That means these are programs where we are addressing the question how to machine, for example, specific materials. And we are addressing this with lectures coming from different disciplines, for example, from chemistry, from physics, from electrical engineering, in order to develop further the skills of the students. I have to say that we are quite successful with these programs. Here in Jena, we have more than 1,200 applications per year. And we are selecting the best 60 students from these numbers. And it's quite international. So we have students in the moment in this program coming from more than 20 countries. We are exchanging our teaching competencies in this field with the university in Karlsruhe and in Erlangen. In order to promote this, we recently established a specific PhD program. It's the Max Planck School of Photonics. And I really invite students from all over the world to apply for this program here in Germany. It's a program with a close collaboration with industry. You will get experience in the work of the best labs in Germany in photonics on one hand side, but also you will get experience in working in industry starting from the beginning of your research phase.
We're joined today by Dr. Andreas Tuennermann, head of Fraunhofer IOF, and we're speaking, among other topics, about education, both internationally and domestically in Germany. In both of your roles, both with Fraunhofer and at Jena, you work not only with current leading industry minds, but as you say, up-and-coming minds. Can you talk a little bit about that environment of knowledge sharing and how, for you, that enhances your research?
Science is based on one hand side on exchange of ideas, and on the other hand, it's also based on competition. I think it is very important for students, for postdocs, and even for seniors to establish their own networks in science and in industry to allow for exchange and competition in science. In Germany, we say it is more interesting to play Champions League as going for a match with your students directly at the door of the seminar room. Champions League in Europe means to play with the best in Europe or even the best in the world. And this is something which is, from my point of view, the main driver of invention, but also of innovations. You need this competition in order to select the best on one hand side, but also promote the best ideas coming out in the discussions with colleagues all over the world.
And part of that equation, too, must be startups and emerging technologies, which are, of course, vital to photonic innovation, but scientific innovation larger than that. Can you talk a little bit about Digital Innovation Hub Photonics and some of the enterprises that have had an opportunity to work since the hub's establishment in 2019?
The idea of the Digital Innovation Hub Photonics, in fact, is that we would like to provide expertise. If you analyze the situation of startup companies, then you learn that, especially in the high-tech area, they are failing because of logistic problems or the questions related to the design of a product, of a real product which could be manufactured at low costs and which is also of interest for customers at the market. With the Digital Innovation Hub, we bring in our expertise from senior scientists and merge it with the ideas of potential startup companies, with the idea to design and manufacture the first prototypes to help them to acquire, for example, VC money. And we are quite successful. In the moment, we have 8 companies in this startup phase, and we started this business 1 year ago, in fact. These are companies like space optics, addressing questions of intersatellite telecommunication systems, companies like ultra gratings, developing, for example, specific fiber and volume Bragg ratings, or company QOJ, which is developing hardware components for quantum technology in communication systems. I think it's not only the money which is important for founding a company. It's really the question of transfer of know-how, and especially the transfer of know-how which is important to generate to design a real product, leading then to some innovation in the field. And with our Digital Innovation Hub, we are supporting these needs in the startup companies.
You mentioned quantum and specifically the transfer of know-how. Just recently, Fraunhofer has opened up and formed its quantum application laboratory. Can you tell us what the lab aims to accomplish and how that supports some emerging global needs in the quantum realm?
Well, quantum technology is a very important point to talk about from my point of view today. We see that we are just in the phase of a second revolution in the quantum physics field. We now have the chance to control quantums, and we have already seen in different labs worldwide that there is an advantage, for example, in applying this know-how to problems in sensing, in metrology, but also, for example, in communication or computing. But it will be very important to find out what are the real benefits in applying quantum technologies in real-world applications. This is one important point which has to be addressed from our point of view. And the other point is that we have to transfer the knowledge from experimental physics labs driven by quantum physicists to engineers and design systems which could be operated in real-world applications. And this is exactly the mission of the quantum labs here at our institute. We are addressing the questions related to the benefits of quantum technologies in real-world applications on one hand side, and on the other side, we are addressing the questions related to the transfer of an optical table in an experimental physics labs to a smart box which can be sent, for example, to space for some communication experiments. So this is something which we are addressing in the moment, and especially we focus on the application fields in communication, in sensing and imaging, and in computing with our work in the moment.
I'm intrigued that you bring up space, not just space optics, but quantum applications in space, because not only in here in North America, but around the world, laser-based applications in space are really rising in prominence and application. But with that acceleration, we're also seeing now some of the stress and the strain that optical components are facing in such an extreme environment, especially without much precedence. My question for you is, what role can laser-based technologies play, not only in ranging applications, but also in improving the quality and usability of optical components that are being used in space?
In the next years, it will be very important to apply remote technologies for Earth observation systems. There are challenges related to environmental monitoring, to the development of weather, for example, but also questions to find resources on Earth. And for all of these challenges, it is important to apply optical technologies in these remote sensing applications. So this is one important application, but there are several others. We have, for example, also a small project which is related to the acceleration of spaceships using laser systems, and where there is some specific interest from NASA and the European Space Agency. For all of these applications in sensing, metrology, but also in, for example, funny or exciting schemes like these acceleration of spacecraft, it will be very important to have laser systems available, which are quite robust on one hand side, and on the other hand, which are very efficient in operation. Efficient means in this case transferring electrical energy in photons. And I have to say that I'm a fiber laser guy. I started my work on fiber lasers in the beginning of the 90s of the last century. And I developed the first systems operated at a few 10 milliwatts. Then systems followed operation with operation output powers in the range of 100 watts, kilowatts. And in the moment, we are talking about several 10 kilowatt in operation with diffraction limited beam quality. There are challenges in handling these powers, not only in space, but in space it's going more difficult. And the unique properties, especially of fiber lasers, are supporting these applications in space, because you don't have any free space optics. You don't have these problems related to alignment specifications and so on. I think it will be very important in the next years to develop further laser technology with a specific focus on fiber laser technologies due to the unique geometry on one hand side, but we also need specific optical systems like telescopes with coatings, for example, which allow for high power operation, long-term stability in reflection, for example. These are challenges we have to address in the next years in order to support the needs of the communication technology of the agencies monitoring the environmental situation, for example, or even programs related to the spaceship development of the next generation.
Is there a sense of pressure that you face in the sort of on the hard science end from industry, from space applications, to get this technology right and get it right quickly?
Well, this is something which addresses the question of strategy. It's not only strategy in research, it's also strategy concerning building up own competencies in order to allow the manufacturing of space-qualified components or systems. And in the past years, we have developed here at Fraunhofer, in collaboration with our local partners, technology platforms, which provide unique properties, which especially address the challenges of the application under harsh environments, and especially address the question of the application of these systems in space. So we have built up some fiber laser technology center, as already mentioned, where we have the chance to design and manufacture low loss fibers, which are, for example, radiation resistant. We have established freeform technologies up to diameters of 1 meter, which allow us to build up telescopes, for example, intersatellite communication, but also for Earth satellite communication systems. And in addition, we established a technology platform related to micro-nano optics, where we have the chance to build, for example, unique gratings for spectroscopic instruments. We recently launched, for example, a system to the ISS, which has been installed there. This is the so-called DESIS telescope and spectrometer, where we combine all of these different technology platforms in order to come to an optical instrument to be used in space with some unique properties.
You talked a lot about fiber lasers, and for you, that is a tool that has been really thematic in your development, but it's also quite a promising tool, not just for space, but for really many extreme environment applications. Can you talk a little bit more, I suppose, about fiber lasers and what those have meant to your development and what role they were going to play in the future here?
Well, the fiber laser geometry has some unique properties concerning the thermal optical behavior. If you have a solid-state laser operating at high powers, you normally see so-called thermal optical effects, which are limiting the beam quality when rising the output power. And within a fiber laser, you have the advantage that due to an intrinsic waveguide structure, the beam quality is conserved, even at high output powers. This is an intrinsic advantage of this specific laser geometry. And there is a second advantage, which are the unique cooling properties of the device. If you have fiber laser, a solid-state laser in a fiber geometry, then of course you realize some optical pumping of this device. And this optical pumping is normally based on the application of diode lasers, which are adapted to the absorption bandwidths of the doped material. But there is a Stokes deficit between the pumping wavelengths and the emitted laser radiation wavelengths. And this results in a heating of the fiber and the so-called thermal optical effects. And due to the situation that the fiber is almost only surface and has no volume, the cooling properties of the device are also good. So you have two key advantages due to the fiber geometry. It's on one hand side the waveguide structure, which conserves the beam quality, and the other hand side it's the optimum cooling due to the high surface to volume ratio within this kind of geometry. And this allows us in the past to scale the output power from several milliwatt level up to 10 kilowatt level or even higher values in single mode operation. These systems are now scaled from an individual emitter close to the damage threshold of the fiber laser material, which is in general fused silica itself. So the power densities you have in the material are close to the damage threshold of the laser material itself. So what is the possibility to scale it further? And we have developed in close collaboration with Nobel Prize winner Gérard Moreau a new scheme. And this is the technique of coherent combining. And with this technology, we are now able to scale the output power beyond the damage thresholds of the individual fiber lasers by coherently combining several emitters and conserving with this approach the beam quality. So we think that we will be able within the next years to scale the output power for diffraction limited beams at 1 micrometer, for example, beyond the 100 kilowatts level in average power. And this is something which will drive completely new type of physics, for example. We think that there will be the chance applying these type of lasers for novel type of particle accelerators to be used, for example, in cancer therapy. Or these type of lasers could be used, for example, to drive a spacecraft and will allow us, hopefully, to go for planets, other planets within our system. I think there is a bright future which opens up due to the application of this unique laser geometry. And I think we will see very interesting results coming from different labs all over the world based on fiber lasers.
Perhaps due to the diverse range of applications for not only fiber lasers, but all lasers, laser safety, especially in laboratory settings, has sort of emerged as a field of its own, or at least a prominent subfield within laser technology. How do you and your colleagues view this increased focus, and how does it weave into the work and the research that commences at Fraunhofer and other institutions?
Well, laser safety is and, of course, will always be an essential part of our daily work. We have to live with the challenges of high brightness laser sources and their application in the labs, but also in real-world applications. Of course, it is necessary to push the safety equipment also in the developments to support also the application of high-power lasers in different fields. We are actively working in safety commissions, for example, in order to address the requirements of the next generation lasers. This is something which is important. On the other hand side, it is also important to think about new solutions to overcome fundamental problems related to the question of laser safety. We are presently working also on lasers which are called, due to the emission wavelengths, eye-safe. We are scaling these type of lasers also to the kilowatt regime and beyond. Of course, these lasers are not eye-safe anymore at these power levels per definition. But on the other hand, for example, scattering problems of light are reduced with respect to safety aspects when you compare this with visible light sources or near-infrared light sources. I think we have to do both. We have to develop further laser safety equipment, but we also have to think about new type of coherent light sources where we have reduced safety problems related to the application of these type of wavelengths.
I suppose it should be of no surprise that Fraunhofer is leading the work in this area. I'm curious, as part of the Fraunhofer network, you have unique access to work with some of the additional Fraunhofer Institutes, and there are many of them. Can you tell us about sort of the nature of the Fraunhofer network and the opportunity it creates both for yourself as well as your colleagues?
Well, the idea of the Fraunhofer Society is, in fact, that we support the German and European industry in developing innovations. And this is our key mission. And in Germany, we have established something like 70 Fraunhofer Institutes, each of them with a specific field of work. And that means that there are specialists within the Fraunhofer Society coming from different fields of disciplines. And this is a real advantage in our community, that you will find a worldwide leading specialist in any area within our group. And of course, this is a reason why the collaboration within our Fraunhofer Society is quite successful, and why we really promote this collaboration. When we are talking, for example, about the coating of polymers, for example, then you will find a specialist in polymer technology within the Fraunhofer Society. You will find also a specialist doing deposition, physical vapor deposition of dielectric materials in order to reduce, for example, the reflectivity of an optical lens made from a polymer. The collaboration within Fraunhofer is important, especially if you think cross-border. If you address questions which are not in your own field. And in this situation, you have the advantage that there is a colleague formed by a similar culture, but with an expertise in a different field. And this is the reason why I love to collaborate with my colleagues within the Fraunhofer Society worldwide.
We're speaking with Dr. Andreas Tuennermann, head of the Fraunhofer Institute for Applied Optics and Precision Engineering. And it's been a busy summer at Fraunhofer IOF, and I want to end with a future-looking question. This summer you have successfully introduced a hybrid manufacturing process for welding. There's been work in the development of light scattering measurement techniques. What's on the docket? What can we expect from Fraunhofer IOF as we move into the fall?
I think based on my colleagues here, on the work of my colleagues here in the Institute, we will see several innovations. In the moment, I would expect that a very interesting topic will be the application of a new type of fundamental optics in imaging applications. We are working on optical systems which are not inspired by the human eye. So what is the main idea of this research work? In nature, there have been developed more than 20 different eye principles during the evolution. These are quite different. Most of our technical instruments we are using in optics today are inspired on the human eye. So you have a lens, you have some free space propagation starting from the lens, and then you have some kind of imager in the eye. It's the retina. The eyes in nature are quite different with respect to the human eye. Think, for example, about the eye of the insects. These are based on the so-called facet eye principle. There are several lenses attached to each other. Then there is the formation of an image based on the small images taken from the different lens systems within the eye. There's a real advantage of these type of optics, especially if you think about the thickness of the optics, for example. This facet eye principle has been developed in order to realize small imaging systems in nature with a low weight. Because insects should fly, especially for applications in industry, but also, for example, in consumer electronics. It is important that you take care about the volume of the optical system within the whole system. For example, if you think about your mobile phone and the applications of camera systems within the mobile phone. We think that the application of the facet eye principle will revolutionize the type of optical imaging in different fields. And if you ask now about new research results coming up from our labs in the fall of the year, I think we will present some very interesting work, most recently on new imaging systems which are small and on the other hand provide a very brilliant image for applications in different markets.
Dr. Andreas Tuennermann, thank you so much for joining us today.
Thank you so much, and we are looking forward on a bright future in photonics.
Join us in January for the inaugural Photonic Spectra Conference. 4 days of online presentations spanning lasers, spectroscopy, optics, and biomedical imaging. 60 presenters all in one place, focusing on the latest in applications, trends, and advancements. Registration is free. January 19th through the 22nd, right here with Photonics Media. Visit photonics.com/pscinfo for event details.
Let's move now to the nanoscale, where applications in nanophotonics are supporting science's quest for the information necessary to develop cures and vaccines for a range of infectious and non-communicable diseases. Certain nanophotonic applications, like ultrasensitive biosensing and nanoscale lasing, rely on a narrow spectrum of distinct light wavelengths, and to achieve these spectrally narrow responses, the systems use periodic nanoparticle arrays. Now, typically, these nanoparticles are of a uniform size. Not always, though. An international team from the University of New Mexico and the Autonomous University of Madrid has introduced a method to apply periodic arrays containing nanoparticles of different sizes, rather than the more conventional arrays, to generate coherent light of desired colors. Here to discuss that work and more is Alejandro Manjavacas, assistant professor at the University of New Mexico and primary investigator in the Theoretical Nanophotonics Group in the UNM Department of Physics and Astronomy. Thank you for joining me, Alejandro. First and foremost, the work we just mentioned, now that's a significant advance in fundamental physics. Tell us more about the significance of the work. What makes it so distinct?
The main advance that we have forward in our work is the fact that periodic arrays have been used for a long time because they have this nice property, which essentially is like the combination of the optical response of each of the constituents, each of the particles that make the array, together with, the ordering, this periodic array ordering, gives rise to some new resonances or new modes, new optical modes that are much narrower and much stronger than the resonances that each of the individual particles produce by themselves. So that has been, studied for many years, is well known. And what we have done essentially is just to realize that if instead of using just one type of particle in the array, you actually combine two particles with different sizes, and then you repeat these two particles periodically rather than just repeating one, then you can get resonances that obviously are narrow as the ones you had before, but actually they are much narrower and much stronger than the ones that you will get for an array with a single particle that is repeated. It's very nice because, we can get much narrower resonances, which are very important for many applications, as you mentioned, but we get them just by doing something kind of trivial, which is just combining, two different sizes. It doesn't require to go crazy and develop a whole new kind of approach. It's just combining two different particles. Now, the extra thing that we get also is that, obviously, when we do theory, we always like to describe these periodic systems as if they were infinite, because that makes our modeling much easier in the sense that we can always impose what we call periodic boundary conditions, and then we only need to, if you want, model one unit cell. And we say, okay, everything that happened on the, on each side of this unit cell has to be periodic. It's going to happen over and over and over. But in reality, when one of our collaborators go to the lab and try to fabricate one of these systems, obviously it's going to be finite. They cannot fabricate an infinite system. And then obviously they need to fabricate a system that is periodic, it's finite obviously, but it's as large as they can. And then, that imposes a limitation. Imagine that they can fabricate, let's say, 1 million particles by 1 million particles. So that number essentially limits the response of the system. So we are always predicting a response for an infinite system, and they are always fabricating something finite. So what we want is not only to get very strong responses, very narrow responses, but we also want that those responses survive, from the theory that we predict for an infinite system to the actual realization in the lab that involves a finite system. So the extra bonus that I was mentioning that we have found is like by combining these two particles with two different sizes, not only we get narrower resonances, but actually we have demonstrated that they, when you go to the lab, you actually need a smaller number, or if you want, you need a smaller array to reach those predictions that we have made for an infinite system, as compared with the case of a single particle. So I'm kind of summarizing what we have, the main advancement of our results are that first, we provide a very simple way to get much narrower resonances, and at the same time, we make those resonances to be, or those systems to be much easier to be fabricated because they don't require to go to very, very large arrays.
So we talked in the introduction here about the applications in biosensing, not only with your work, but with nanophotonic applications in general. And so what we're doing here with your work is we're designing more sensitive optical biosensors with a smaller footprint. Can we talk a little bit about biosensing? What doors is the work opening in that area?
So biosensing, optical biosensing, essentially is the idea of detecting molecules, detecting compounds that have relevance in biology, which can be, for example, viruses, could be like different molecules, gases, like things that have a value, and then we want to be able to detect them with light. And then obviously any, optical biosensor works on the idea that you have a system that has a certain resonance, has an optical resonance. So when I shine light of the appropriate wavelength, I'm going to get a strong response. But then the system has to be such that now when we place something in the vicinity, like for instance, one of these molecules we want to detect, the presence of that molecule has to change the optical response of the system in a way that when we interrogate the system with our laser or our light source, we are going to detect a change on the response. And then by detecting that change, we know that there is the molecule or the analyte that we want to detect is nearby. So obviously, based on that, it's easy to understand that what you need to have a very nice and a very efficient optical biosensor is you need a system that has first a very strong optical response, so it interacts very strongly with anything that is placed nearby, but also that optical response has to be very narrow, because that's the way we make sure that when we place something nearby and it's interacting with the system, then it's going to change the response. If you have a very broad response, you are not going to be kind of seeing any even if there is a change, the change is not going to be detectable. So then optical biosensing requires systems with a strong response and narrow resonances. And obviously, our work can help because, as I have explained before, we have put there a nice and simple approach to make the resonances of periodic arrays much narrower and also requiring a much smaller footprint, which is another very important aspect. Now, we want to have sensors, optical biosensors that we can integrate, that we can make them small enough so they don't require bulky components, and then they can be just fabricated in a massive way, and then they can be delivered and used as much as possible.
Tell us a little bit about next steps of the work. We've made progress here. I say we, and I mean you. You've made progress here, starting from point A to point B. Where do we go with point B to point C?
So in my group at the University of New Mexico, we have been very active on this topic of periodic arrays. We have been working a lot on trying to understand, the nature or the fundamentals of the response of this system. One thing that we have been kind of working a lot over the last years and kind of was the reason why we went to these systems that we studied recently was we were very interested on kind of understanding what happened when you have these periodic arrays and you start, making them more complicated. As, for instance, in this case, adding a second particle in the unit cell. Something that we have been working after as a kind of a follow-up of this work has been to understand kind of the other way around. So what if we start with a periodic array that has just a single particle and is repeated periodically in all directions, and now we start removing, one particle every certain number. So essentially we induce or we introduce a periodic array of vacancies in that periodic array of particles. And kind of following the same ideas as in the previous work, we are finding that those systems, or just by making these holes, if you want, on the array, you can induce new lattice resonances with very interesting properties. That's kind of is a follow-up of the work in which we are kind of now working a lot. Another thing that obviously we are very interested on is just to verify experimentally the results that we just published. We are a theoretical group, so we don't do experiments, but we collaborate with many groups that actually do experiments. And now we are collaborating with a group at the Universidad Autónoma in Mexico, and also with another group from Czech Republic. We are collaborating with them to actually, one of the groups is going to fabricate the arrays, and the other group is going to measure the optical response. So we are kind of designing a system that can be fabricated because, what we publish is theoretical, so it's very or less demanding in terms of we can choose the parameters that we like. But then once you go and try to fabricate, obviously each lab has some limitations. They have some materials they work with. They have some techniques that they have been developing. So what we do is to adapt our theory to essentially the limitations they have and design a system they can fabricate, and then the other group can measure. So those are kind of the two follow-up projects we are working right now in this topic.
We're joined by Alejandro Manjavacas from the University of New Mexico and the Theoretical Nanophotonics Group at the university, joining us from snowy Albuquerque today. You mentioned theoretical nanophotonics, and that's interesting because it opens you up to do work in a broad spectrum of problems involving light-matter interactions. Off here, we talked a little bit about some of the work that you have done and that's ongoing and forthcoming with the group. Tell us a little bit about the Theoretical Nanophotonics Group and some of those projects.
So, as you say, one of the things that I really love of working on theoretical nanophotonics is that, we can actually explore a very broad range of phenomena. all of them obviously connected to the fact that at the end of the day, what we are interested on is to understand how light interacts with matter at the nanoscale. And the nanoscale has this kind of very interesting aspect, that is that the light in the visible range has a wavelength that is of the order of, let's say, between 400 and 700 nanometers. And that is actually the size, those nanometers, those 500 nanometers, are the sizes of the structures that we typically deal with. And then this matching between the wavelength of light and the size of the object makes them, the light-matter interaction at this level very, very interesting and also very different, from the usual light-matter interaction that we see in the macroscopic world, like mirrors or lenses. So when you go down to the nanoscopic world, things are much more interesting, as I say. And then, when you work in theory, it's very easy, once you know how to attack these problems, how to describe those interactions, you can apply that knowledge to a huge variety of problems. And just to illustrate a little bit of the broad spectrum of problems we deal with in our group at UNM, let me just tell you about a couple of projects that we've been involved over the last kind of year or 2 years in my group. On one side of the spectrum, we have been working with scientists from the Metropolitan Museum of Art in New York to understand the optical response of daguerreotypes. For those of you that are not familiar, daguerreotypes are actually the first photographic technology. So it was the first technology that allowed human beings to capture permanently an image. And this technology was invented in France in the 1839s, and then over kind of 30 years was the only way we had to capture images. So therefore it was widely used, and there are many, many beautiful daguerreotypes that were taken on those times. Now, what is amazing of daguerreotypes for us is that, this technology is based on capturing an image on a metallic plate. And at the end of the day, when you just take the picture, if you want, what you get on the daguerreotype is you have a metallic surface, which looks like a mirror, and on that surface, there is an image that is kind of imprinted. And the image is imprinted by the generation or the creation of the small nanoparticles. It's a silver surface, and then in that silver surface, then they grow some silver nanoparticles. And then these silver nanoparticles actually support plasmons. And plasmons are one of the central topics now in nanophotonics. Plasmons are electron excitation supported by metallic nanostructures. So what we discovered in collaboration with these people from the Metropolitan is that actually the image that we see in a daguerreotype is the result of the scattering of light by silver nanoparticles deposited on a silver film, which is kind of the typical system that is studied a lot in nanophotonics, and in particular in plasmonics. So in that sense, you can call daguerreotypes one of the first plasmonic technologies, and it was invented obviously way before plasmons were even a concept. So this research, apart from being kind of very interesting and a little bit off of the typical things that we do, is really important because understanding how these daguerreotypes work is crucial for our collaborators in the Met to develop new protocols to preserve them. I mean, these are very valuable artworks which obviously degrade with time. And then the Met has an amazing collection, and obviously they are very interested on preserving them for the future. So getting this knowledge on how the optical response emerges from these metallic nanoparticles is crucial for them. And you see, this is kind of one end of the spectrum. On the other end of our spectrum, we have been working together with collaborators in the theoretical division in Los Alamos National Laboratory, which is here not far from Albuquerque. I've been working with them on understanding how, the fluctuations of the electromagnetic field can produce very interesting phenomena. So the electromagnetic field fluctuates because there is always a finite temperature, and when we have a finite temperature, we know that the vacuum is not really empty. It's going to have, a bath of photons, and the properties and the quantity of these photons will depend on the temperature. But even if you go to absolutely zero temperature, the quantum nature of the electromagnetic field will make it also fluctuate. So no matter what you do, you're always going to have fluctuations around any object. And those fluctuations actually are at the core of many interesting phenomena, like, for instance, radiative heat transfer, also Casimir forces, which, are kind of a little bit of exotic forces in the macro scale, but they have very, very interesting properties or very interesting consequences at the nanoscale. And there is where we have worked a lot on that topic since many years. And now we are actually interested on understanding how these fluctuations and the forces and the torques that they produce can be used actually to, manipulate nanoscale objects. And in particular, the work we have been doing with them is like to essentially understand that if you have, for instance, one of these nanoparticles we typically look at, and then you make it rotate, you spin the nanoparticle, and now you put another nanoparticle nearby, because the particle that is spinning somehow is affecting the fluctuations of the electromagnetic field around it, then that perturbation of those fluctuations are going to be filled by the second particle. And at the end of the day, what we have predicted is that can be used to transfer angular momentum. Or in other words, the fact that you rotate one particle is going to make the second particle rotate. It's like somehow the vacuum around them were a fluid, and the spinning of the first one will kind of make that fluid rotate, and that will be transferred to the other one. This is kind of a very theoretical and a little bit exotic concepts, but they are actually getting closer and closer to actual technological applications. Indeed, over the last couple of years, there have been a lot of groups working on actually spinning particles, first trapping them with optical tweezers and keeping them in ultra-high vacuum, and then, spinning them, and they have been able to reach limits or ranges of rotational frequencies which start to be large enough to observe some of these theoretical predictions that we have been making over the last years. So I hope these kind of two examples illustrate a little bit of the broad range of interesting phenomena that theoretical nanophotonics in general can study. And, we are doing theory, as I say, so many times our motivation is just very fundamental. No? We want to understand how things work. But in many cases, they have actually close or very fast applications, as for instance the case of the daguerreotype work.
Three very specific and very distinctly different projects underway with the Theoretical Nanophotonics Group. Thank you for joining us, Alejandro, and best of luck this winter as you continue your research.
Thank you. Thank you very much for the opportunity.
That does it for this episode of All Things Photonics. Thank you to our engineer, Alan Shepard, and to Joel Williams with the news. Our featured music is courtesy of betterwithmusic.com. Most of all, thank you, our listeners. As always, you can share your thoughts, pitch us ideas, let us know how we're doing. You can reach us at allthings@photonics.com. All Things Photonics is available on all major platforms, including Spotify, Apple Podcasts, and Google, as well as on our website. Subscribe, never miss an episode. I'm Jake Saltzman. This has been a Photonics Media production.